You know, everything around us, the phone in your hand, the building you're in, the plane in the sky, it's all made of materials that took us centuries of slow, painstaking work to discover. But what if we could compress, say, 20 years of that work into just a few months? Well, that's not science fiction anymore. It's a revolution that's happening right now, right at the intersection of materials science and artificial intelligence.
So, it makes you wonder, right? How do we actually invent the materials that are going to build our future? For centuries, the answer pretty much looked the same. A scientist in a lab, mixing things, heating them up, testing them. Really just relying on intuition and, let's be honest, a little bit of luck. It's an image we all know. But this traditional trial and error method has a massive fundamental bottleneck.
And this diagram here, it shows that bottleneck perfectly. It's this slow, incredibly resource-intensive cycle of trial and error. You mix, you heat, you test, and, most of the time, you fail. It's expensive, it takes forever, and eventually you smack right into what's called the complexity wall. That's the point where there are just way too many variables for any single person or even a team to track and optimize.
So, what's the result of hitting that wall? Well, you get timelines measured not in months, but in decades. I mean, can you imagine waiting 20 years for a stronger, lighter alloy that could make airplanes way more fuel efficient? That was the reality. But what if we could shrink that timeline? What if we could take those decades and crush them down into months? Well, that brings us to what is truly a data-driven revolution. This is where we fuse the core principles of material science with the raw power of data science and machine learning. And here's the difference in a nutshell. The old way relied on just doing experiments over and over again. The new approach, called materials informatics, uses machine learning models to predict the outcome. So the development timeline, it shrinks from decades down to months. And the scope, it explodes from just a handful of tests to screening literally millions of potential candidates. The key idea here is huge. We're shifting from educated guessing to data-driven prediction. Now, this whole revolution didn't just happen in a vacuum. It was built on a mountain of data. Big initiatives like the Materials Genome Initiative laid the foundation by building these massive public databases. You can think of them like giant digital libraries, but instead of books, they're filled with the properties of thousands upon thousands of materials. And all that data, from simulations and real experiments, became the fuel for this new engine of discovery. So we've got the fuel. Now let's take a look at the engine itself. This is the new playbook for how we actually find and design materials today. At the heart of this new playbook is a really core concept in materials science called the MPPP chain. It's actually a pretty simple chain of cause and effect. The manufacturing process, like how you forge a piece of steel, that dictates its internal microstructure. That microstructure then determines the material's properties, like how strong or flexible it is. And finally, those properties define its real-world performance, whether it's actually safe enough to be used in an airplane wing. The materials informatics engine basically takes that MPP chain and puts it on steroids. It creates this incredibly powerful feedback loop. You start with data, you use it to train an AI model, and then that model makes predictions. But here's the cool part. Those predictions get tested, which generates new data, which then feeds right back into the system, making the model smarter and more accurate with every single cycle. And here it is. This is the most powerful part of the whole thing. Machine learning allows us to create a kind of digital shortcut. So instead of going through all the slow physical steps of that MPPP chain, the AI can learn the incredibly complex relationship between the starting process and the final performance. We can now predict how a material is going to perform before we even make it. This is the leap that turns decades into months. Okay, so that's the theory. Let's talk about practice. Where is this data-driven approach already changing the game? I'm going to give you 3 real-world examples. First up, let's talk about analyzing a material's microstructure. What you're looking at here is a microscopic snapshot of its internal structure. Traditionally, a human expert would have to spend hundreds of hours manually poring over images just like this. Well, now a type of AI called a convolutional neural network, or CNN, can pull out all the critical features like grain size and orientation in just seconds, and it does it with superhuman accuracy. Second, we can now predict a material's properties without ever having to break it. I mean, instead of a physical stress test, we can use a machine learning algorithm, something like a random forest model. You just feed it the recipe, the alloy composition, the heat treatment, and boom, it predicts the final strength and hardness. It's a perfect example of completely replacing a physical experiment with computation.
And for our third example, let's look at advanced manufacturing, like 3D printing metal parts. Now, this is a hypersensitive process. Tiny changes in laser power or speed can cause major defects. Well, machine learning can monitor all these variables in real time and predict if a defect, like a tiny crack, is about to happen. This allows the system to adjust on the fly and make sure the part is built perfectly the first time. So yeah, the applications are clearly transformative, but this is still a pretty new field and it's facing some significant challenges. So let's look at the road ahead and the really exciting frontiers of what's coming next.
Right now, there are three main hurdles. First, there's just not enough good data. High-quality materials data is really hard and expensive to generate. Second, the data we do have can be biased. It's mostly focused on common materials, which means the AI has some serious blind spots. And third, there's the black box problem. A powerful AI might predict a perfect new alloy, but if it can't explain the physics of why it works, well, that really slows down true scientific understanding.
But here's the cool part. The frontiers of this field are aimed squarely at solving those exact problems. The future isn't just about predicting things faster. It's about creating autonomous systems for discovery. Think about an AI that actually understands the laws of thermodynamics, working side by side with robotic labs that can synthesize and test new materials 24/7 without ever getting tired.
And these two new frontiers, they directly tackle those challenges we just talked about. Physics-informed machine learning solves that black box problem by forcing the AI to obey the fundamental laws of physics. It can't just give you the right answer, it has to show its work. And self-driving labs, they solve the data scarcity problem by using automated robotics to just constantly run experiments, creating this fire hose of new, high-quality data. What we're witnessing here is a fundamental shift, moving from slow, manual discovery to automated, intelligent creation. And that leads us to a really exciting final question. With labs that never sleep and an AI that actually understands the laws of the universe, what impossible material are we going to design tomorrow?